Welcome to This Explainer. Today, we're diving into what is literally the universe's ultimate missing persons case, the hunt for invisible dark matter. We're going to explore how scientists are using some of the most precise instruments humanity has ever built, orbiting atomic clocks, to track down something that, well, no one has actually ever seen.
To really grasp the scale of this mystery, we've got to start with just one number, 5%. Think about it. Everything we can see, touch, and interact with, from the device you're watching this on, to the earth beneath your feet, to the most distant stars, all of it makes up a mere 5% of the universe's total energy density. The rest? Completely missing. It's made up of dark energy and dark matter. In fact, right at this very moment, our entire solar system is sweeping through a massive halo of this invisible dark matter at a mind-bending 230 kilometers per second. We are literally sailing through a dark wind.
Section 1. The Missing Universe.
So enter our unlikely detective for this case, the atomic clock. Now, we rely on these clocks every single day just to keep our global positioning systems perfectly synced up. But in the realm of high-level physics, an atomic clock doesn't just tell time, it acts as a hypersensitive quantum sensor. You see, because it measures time based on the ultra-precise vibrations of atoms, it is incredibly sensitive to fundamental physical measurements. If the very fabric of reality shifts even a tiny fraction, an atomic clock can actually feel it.
Section 2. Catching the dark wind.
Okay, so how exactly do you measure something that doesn't emit or absorb any light? Well, the answer lies in a mind-bending idea physicists call the portal theory. Since dark matter doesn't interact with electromagnetism, scientists think it might interact with our world through hidden portals. Basically, these portals would allow dark matter to slightly alter fundamental physical constants, things like the fine structure constant. And here's the kicker. An atomic clock's ticking is completely governed by these exact fundamental constants. So, if a wave of dark matter sweeps by and changes the rules of physics for even a split second, the ticking rate of our atomic clocks will change right along with it.
That brings us to our first prime suspect, which scientists call clumpy dark matter. Imagine dark matter forming these massive topological defects, or clumps. As one of these giant clumps sweeps past an atomic clock at galactic speeds of around 300 kilometers per second, the fundamental constants inside that clump are actually different, and this causes a transient glitch, essentially a temporary shift in the clock's frequency as the clump passes right through it.
Then we have our second suspect, wavy dark matter. So instead of massive clumps, this model suggests dark matter is made up of ultralight classical fields. Because these fields are so incredibly light, their wavelengths can literally be the size of entire dwarf galaxies, and they behave like a massive wave oscillating back and forth. If this wavy dark matter washes over our clock, it would cause those fundamental constants, and therefore the clock's ticking, to continuously oscillate right along with the field's frequency.
Now you might be thinking, wouldn't a single clock glitching just look like normal internal noise? Absolutely. But imagine we set up a global detective net of perfectly synchronized clocks. If a dark matter clump hits the first clock, it desynchronizes. Then, as that invisible clump travels the distance between the sensors at galactic speeds, the second clock eventually gets hit and desynchronizes in the exact same way. Finally, both clocks resynchronize as the clump fully passes by.
And this creates the exact sequential footprint that scientists are actively hunting for. As you can see, there's a distinct hump in the data here. This represents the time difference between two spatially separated, initially synchronized clocks. The difference spikes right when the dark matter wall hits the first clock, it stays high as the wall travels between them, and then drops right back to zero once it passes the second one. It is essentially the smoking gun for clumpy dark matter.
Section 3. The GPS stakeout.
So here's a fun fact. We actually already have a massive network of atomic clocks floating right above our heads. Scientists are using our GPS satellites to run a literal stakeout for these glitches right now. But relying on this current network has some pretty critical flaws. The biggest issue by far is ionospheric noise. Solar wind, which is basically just fluxes of electrons shooting off the sun, can perturb the GPS microwave signals as they travel through the atmosphere. And get this, the velocity of this solar wind is remarkably similar to the speed of those dark matter sweeps. That means totally ordinary space weather can perfectly mimic a dark matter signal. Add in the fact that public GPS data is only recorded every 30 seconds, it suffers from multipath interference, and it uses opaque black box processing methods, well, you can start to see why scientists are desperately looking for an upgrade.
Section 4. The ultimate space constellation.
To fix these earthly blind spots and bypass that atmospheric noise entirely, researchers are proposing a massive upgrade to our cosmic dragnet. We need to move away from just repurposing old navigational satellites and start launching dedicated space missions. Let's compare the current setup with this proposed future. On one side, we have the current GPS mission. We're stuck using older microwave clocks, dealing with tons of atmospheric noise, and relying on really slow data sampling. But on the flip side, we have the proposed CubeSat constellation. These are relatively inexpensive, miniature satellites equipped with highly sensitive, next-generation optical clocks. Because they operate out in the true vacuum of space, they are completely free from Earth's atmospheric interference, and they can beam down high-speed, dedicated data specifically designed to hunt for dark matter. It's a total game changer.
And by putting these high-performance optical clocks into orbit, we can do something really incredible to hunt down that wavy dark matter we talked about earlier. By actively varying the distance between two satellites and altering their angle relative to our galactic velocity, scientists can basically sample the dark matter wave at different locations. This lets them map out the correlation of the dark matter fields across vast distances, pushing our sensitivity limits way beyond what is even remotely possible here on Earth.
There's another incredibly exciting proposal derived from our sources called the PHOCOS mission. This brilliant idea involves placing a satellite housing a high-performance atomic clock into a strongly elliptical orbit. So as it travels along this elongated path, it's constantly varying its distance and orientation relative to a terrestrial clock back on Earth. This creates a highly dynamic, continuously shifting net, giving us a completely unique geometrical angle to try and catch that dark wind.
But here is an absolutely crucial point. The space-based net isn't just limited to optical clocks. As the research notes, we can easily extend this concept to other quantum sensors too. For instance, we could deploy orbiting magnetometers right alongside the clocks to hunt down specific dark matter candidates, like axions. By combining different types of quantum sensors out in space, we can effectively cover multiple portals through which dark matter might be trying to interact with our universe. We get to cast a much wider net.
So, as we wrap up this explainer, I want you to try something. Look up at the night sky tonight. Realize that we are currently hurtling through a vast, invisible ocean of dark matter. And ask yourself, what invisible cosmic forces might be altering the very fabric of time around you right this exact second? By finally putting our most precise clocks into the absolute silence of space, we might just be on the verge of hearing the universe's deepest secrets. Thank you so much for joining me, and keep questioning the universe.